been exposed to an awful lot of things, but I hope that you are able to pick up some of the concepts and ideas. I don't get the impression that I'm really trying to say that everything is layered no cross flow, but I can tell you after observing a lot of your data and looking at a lot of performance that there is quite a bit of it, so you should be aware of it and to try and take it into account. And again, the main point I'm going to try and make is when you're doing forecasting, I think you're obligated to look at a forecast with and without cross flow. And part of this example is going to be exactly that. We're going to make a forecast for a gas system, one well. You get 2 layers, a forecast without cross flow and then a forecast with cross flow. And we're going to work the problem by hand, at least in this session here. And then I'll give you the numbers that we got out from program 71, the gas deliverability forecast, and it would be appropriate for the person who is running that program now, take this data and go ahead and run it as a layered no cross flow system. I don't know if you've ever had a chance to run it, have you? 7151 in that mode? Okay, you ought to do it because it takes a little bit of skill and manipulation and understanding, and if you have any problems at all, call Dave Reese in Bartlesville. He's considered the expert there with that program. And you know, I don't do these things myself anymore. I had Dave run this, okay? And then I'm also going to give, I'll give you those values that I got so you can have a chance to check it, and then you'll at least be in a position, if anybody else wants to run some type of problems on that, they could use it. We tried to take the model, like I mentioned before, to run it, demonstrate like we did in the original layered no cross flow paper. Got identical answers, but there's a little confusion about time. The times, like what we're going to do here on this example, I want to keep it simple. The rates that we're calculating are going to be the time at the end of the year instead of the midpoint of the year. It doesn't make that much difference, but we're going to try and be consistent. And it's going to be a 2-layered system, and we could possibly have it to where we can have one half the room do layer 1, the other half the room do layer 2. You tabulate the values on the board or on one of these overheads, and that may speed it up. Would you prefer that way instead of having to do it all, or would you really prefer to do it all? Any comments? Come on. Excuse me? Okay, I like the idea because it speeds things up. We get that out of the way. We're going to try another example I hope to get to just to demonstrate. We're going to take the ratio Q max over G sub I and put it in terms of reservoir variables. And I want you to see how you can get the ratio of 10, which is a very unfavorable situation with regard to forecast, by first here we're really going to vary it primarily by the permeability, but I'd like for you to see how you can get the same ratio with different skins on each layer, and the same ratio with different everything being equal except the volume. And the fact that the thickness enters into the problem, the best way to get the volume as a ratio difference of 10 would be to keep permeability, skins, and thickness all the same, and just vary R sub E. And you'll see you'll get differential depletion even when the thickness, permeability, and skins on each layer are exactly equal. You get the same type of behavior. So you don't get hung up with the concept that I have to have a contrast in permeability for this to be a factor. Okay. And after we work that problem, I'll show you some of the results that we did when we were doing infill drilling, but I don't want to go that far on this one. If we can get this one out of the way, then I'd like to at least start on the example of a single-phase liquid, two-layer system, where we're going to make a forecast on the original well on 40-acre spacing, and then we're going to drill an infill well at the 20-acre spacing, and then we're going to drill 2 more infill wells to a 10-acre spacing, and show you what the rate time profile looks like, and then compare it to one that's published in the papers. You're all supposed to get a set of these papers. If you don't have any, you ought to get one, but you ought to look at the paper on changing concepts in carbonate water flooding, West Texas, Denver unit, and it came out in June of 1974. I think that's the one, either that one or a subsequent one that shows the type response they were getting from infill drilling. I think it is a subsequent one. I'll get that one later. But what the problem is going to be, the slope of the back pressure curve is going to be 1. That don't look like 1, but it is. And the flowing pressure, if we had a flowing pressure 0, what value B should we have? We went through this before with a table of B's as a function of slope of the back pressure curve. Does anybody remember what it ought to be for a flowing pressure of 0? What it should be, if you go back and kind of review the material, I'm going to have to use the red here because I just want to put it in. It should be a B of 0.5. We don't want to use that one, but that's what it would be if you'd assume a flowing pressure equals 0. Okay. What we're going to do with this problem, though, is we're going to have a back pressure or flowing pressure of 100 pounds as compared to the initial shutting pressure of 1,000. So this ratio is 0.1, and the B value that you get from that, it's a very good one to use as a general value of B for a single layer system, gas wells, is a limiting case that if you at least keep it that low, you're going to recover 90% of the gas in place. Okay. If you don't keep it that low, you can't get 90%. So the B value that we're going to use is going to be 0.4. The reason I want to point this out is you're going to look at the equations and so on and so forth, and this ratio here is in terms of Q max over G sub I. Well, when flowing pressure is equal 0, Q max is nothing more than absolute overflow potential. Okay. And G sub I is the original gas in place. Well, we're going to be operating at a flowing pressure of 100 pounds. It is a flow off the stabilized curve, the pseudo steady state equation, at a back pressure of 100 pounds. So your Q sub I, or the Q to use in this ratio, is the Q at a flowing pressure of 100 pounds. So let's say this would be 11,200,000 at Q max, or 0 flowing pressure at 100 pounds. It's going to be 11 million, period. Okay, there's not much difference, but you have to at least understand that that's the way you should be doing it. The same way with regard to if the flowing pressure on your material balance were 0, you would recover the original gas in place. But if it's going to be a flowing pressure of 100 pounds, this is going to be the G value that should be used in this ratio. So I just want to alert you to that, because you've got to use this in working your problem. Okay. It's an important concept to understand. Now, when you get into single-phase liquid, it's linear equation, you can include the flowing pressure in your calculations. That's why I wanted to work the example on, because it's always exponential, regardless of the back pressure. Here, you know, the back pressure indicates that for a PWF of 0, you get 0.5, and for PWF of 100, you get 0.4. If I had an exponential or single-phase liquid problem, and if I had any back pressure, they're all exponentials at any back pressure. So that's why I'm trying to point this out at the beginning. And I went through the exercise and I worked a problem, the same identical problem, with the assumption that, well, I'll use a B of 0.5 and the Q max and the gas in play. How much difference? You know, it makes a little bit of difference. You won't compare 7151. Okay, these are the variables that you need to use in your problem. Let's split the room. This side here is going to work layer 1, and this, no, the other way around. This side here is going to work layer 1, and that side can work layer 2. You're going to find out layer 1 doesn't last very long. So less people working on layer 1. And these are the variables. So you can start to calculate gas in place for each layer, okay? And also the coefficient for the back pressure curve for each layer. And this coefficient here is nothing more than a pseudo steady state equation with the delta P taken out of it. Where the units on the Q are going to be in terms of standard cubic feet. Work on it, kind of compare answers, and have a spokesman, and we'll see if we end up with the same answer that I did. I had Dave Reese and Tom Thrasher work on it, and then I checked their numbers later to make sure I wasn't embarrassed. You know, because once you get embarrassed and you have to try and work through the numbers spontaneously on your feet, you get all confused and embarrassed, and I don't want that to happen. Which is about 6.32 billion standard cubic feet, which that's the number I remember. Okay, what would G1 be now? Have you got the number?
Yeah, 5.79.
Okay.
Assuming set is equal to 1.
Right. Let's keep it simple. You know, we just assume in a recovery factor. I'll put the equation up here on a bit. Now that everybody's finished with that, let me put it up so that we could make sure that we're coming from the same place. Now these are the equations that you're going to use. Next, you need to make sure that G is equal to G sub I times 1 minus PWF over PR sub I. Now, you've kind of given this problem to an engineer in Bartlesville to help me. The assumption of Z equal 1, unfortunately, he used also in the beta G for original gas in place, and that wasn't the intent. The intent is to keep this simple. You know, that's the recovery factor. Don't worry about Z. If you think you want to improve it by including the Z, that's up to you. But it isn't going to make that much difference.
Actually, that's includes this number includes set, assuming set equals 1 at 100 psi and set equal to 0.835 at
let's use Z equal 1 for the entire thing. So again, we start off with the right number. Again, simplicity. Okay, let's not overcomplicate the problem. If you want to get more sophisticated, you can run the 7151, and after you get those answers, then you can run a model. You tried to show you yesterday these real simple equations. I can get an answer within real good engineering accuracy, almost identical numbers. So you don't have to overcomplicate the problem. But excuse me.
1.69.
That will make us a 6. Okay. All right, what about C1? Have you got this?
11.2.
Okay.
11.1.
Okay, and that would be standard cubic feet per PSI squared per day. Okay, right. Okay. Let me check that. Oh, I think those are. Okay, I got 5.688. Let's use that just again so we can check our numbers, all right? I'm not trying to necessarily improve accuracy. I just like to have your things to be comparable so that we're starting out in the same place. And the C value got 11.12 exactly. Okay. All right, from the other group, the original gas in place for the less permeable layer. 8.4. Let me check. Yeah, that sounds like a more consistent number. 12.64. Okay, that's what I got too.
This formula that you put up, is that in Fahrenheit or Rankine?
The Fahrenheit. You got to add 460 to it. The temperatures in Fahrenheit, excuse me, yeah. Okay. It's 100 degrees Fahrenheit on the original data.
Yeah, but in the formula, it's not.
It's Rankine, right. You have to add 460. A G1, using just the simple ratio of 1 minus PWF over PRI. Yeah, it'd be 90% of that number. Okay, I got 11.376. We'll just. Yeah, I think this is probably a 0 in there. That's why I was carrying to 3 significant figures. And C2? The temperature I gave you was Fahrenheit. The temperature in the formula should be degrees Rankine. Right. So you had 460 plus 100. Sorry about that. That's what I got. Okay. We'll be starting with the same numbers. Now again, what we need to do here next is just go ahead and make our forecast. Layer 1, layer 2 is a function of time in years. I'll give you the time intervals because you don't want to do them all. 1, 2, 3, 4, 5, and then increments of 5. 10, 15, 20, 25, 30, 35, 40, 45, 50. In years, those are years, okay? And when you're going through the calculations, this ratio here of Q over G, if you just include your 365 here, then you can just make the calculation in years, okay? Because otherwise this is standard cubic feet per day over standard cubic feet in days per year, and then go ahead and do it in terms of years. And you know, you have everything now. You have the QI. This is the same as that. Don't let this confuse you. This isn't the Q max. You got to be consistent. This is QI, this is QI, that's G, and this is the QI that you have to calculate. Yeah, we have to calculate that number at a difference in pressure squared of 1,000 squared minus the 100 squared times the coefficient will give you a QI, okay? I almost skipped a step. So I think we need to then put we have two more numbers to get, I guess, before we go ahead. Oh, I got 911. Okay. I wonder what I did wrong. Again, I got 911.
Probably depends on the decimals you're using.
Okay.
If you round off C to 0.92, you probably get it, instead of using 0.919.
Let's use 910. We'll average the two numbers, okay? Okay. Now we're ready to go ahead and do the production forecast using this equation here. You've got the B, you've got the QI and the QI and the G. You know, just go ahead and do it in the increments of time, and remember to put the 365 in there. The type curve, and I think this is on the same scale, and let's just look and see if you take this, then you, I can't, let's see, here's a 0.4. That shouldn't be any surprise that it exactly overlays the 0.4, because that's what we used in our calculations, of course. And your other one is also going to fit a 0.4. But it's going to be a lot further down, because it would deplete so fast that we lost that early. You know, you'd have to increase or decrease your time increments early to 1 day and 5 days and 10 days in order to get some of the points out in here. on that real high perm layer. But you want to discuss what kind of a value will be that this. Don't give an awful lot of weight to the real early time, but what would. Well, I can't see I'm keeping the axis because you got to be careful at angle theta in trying to get matches. But it's in the region of the high B's, okay? Don't expect ARPs to exactly fit every single situation. It can't because it's not that rigorous. But don't also throw it away. Like for this, if you were to try to use a B of 1, you're going to run into some. You could take the same identical equation, take these. Add up the QIs and the GIs and say I'm going to use a B of 1. Your forecast is going to be tremendously different than what you got by doing them individually. And say, oh boy, this don't work. But that's not the a limiting value. I told you the other day that I would use. In fact, I tried it on this problem. If I use a B value about 0.8, it's the early time I'm interested in. I get reasonably close to what I did by hand, okay? It's the early time, and you can see the other one kicking out. Don't let that worry you about accuracy or precision. Remember what you're trying to do. You've identified a layered no cross flow, a high B value, the volume ratio, and that it's a layered system. And don't ever use a B value of 1 in any forecasting calculations because it's theoretically impossible. If you look at the equation, mathematically, you finally get there. What do you get when you subtract 1 from 1? Right here, you get 0, and you can't divide by 0. So it's impossible. Okay, I hope the exercise was informative, interesting. You see how easy it is, really. The second part that I'd like for you to work out, we'll have the layer 1 people here and also the layer 2 people there again. We're going to calculate the cumulative production to the end of year 5, and then you're going to calculate the pressure in the layer, or the P over Z in the layer, okay? And let me give you the equation that you ought to be using. And we'll just put the 365 in here now. It's going to be in years. Okay. And so you're going to solve for the cumulative production, and you're going to come down and you're going to use this equation here because I've got the plot in this form. I'm going to give you that the PI over ZI is equal to 1200 psi. That's was the original Z that you used in your gas in place calculations, and the original pressure of 1,000. Okay, so each of you go ahead and calculate the at the end of 5 years what your cumulative production is. In using the material balance equation and your PI over ZI equal to 1,200 pounds, each of you calculate your layer pressure. Now that's for the rate equation, the G sub I, the ratio. This is the true material balance equation. This is the initial pressure and the gas in place down to 0, okay? You could play with that if you wanted to, but you'd have to define things differently. You'd have 900 pounds instead of 1,000 pounds as the drop between. You know, because that is nothing more than a ratio of the PI over ZI divided by G, and if you stayed consistent, you'd still end up with so many pounds per BCF as that number in parentheses. You know, this way here you can work either direction. You're going to get the right answer if you stay consistent. Okay? Right, do you have the... Right. You for layer 2? Okay. I got 1059. That's close enough. All right, that's the differential depletion that is occurring in this particular situation at the end of 5 years. You got 1,000 pounds in the low perm layer, and you've got about 300 pounds on the high perm layer. And you go in there and you run RFTs, and that's what it's going to show. For some reason, you only recorded the pressure in the high perm. Let's say your low perm layer is on top, and the other layer was wet, or you didn't drill so deep, so on and so forth. You get a shutting pressure of 1,000 pounds on one well, and the other well shows only 295 because you got a commingled shutting pressure. We got a barrier, we got a fault. We have potential for infill drilling. We're not draining the field. See, this is what's happening. People that are taking some of the data, like the people in the Bureau of Economic Geology, they've got this type of data, but they're not interpreting this as layer pressure. That means pods. You know, there's aerial discontinuities, and let's do infill drilling. Remember, one of the things that I tried to demonstrate with that ratio the Q max over the G sub I ratio, if I multiply number or the QI by 2 in the numerator and denominator, I'm at the same place. My differential depletion will be the same at the same Q. Now I may recover it faster, but that's pure acceleration. You can't justify the process on one of increasing reserves. And we have a plot of this over its entire length of this problem. I've added on that, this is what the differential depletion is going to look like with a continued cumulative production. And this distance between here and here and here and here is in proportion of 2 to 1. This represents the volume in the low perm layer, and this represents from here to here the volume in high perm layer. Or take the divider between those two, and that's it. But I wanted to carry you not only through the rate time, but an opportunity to calculate pressure. You got P over Z, you can convert that to pressure. If you have Z factors, it's not going to make much difference. That plot came out of 7151, and it really don't make any difference. Like you saw, the rates are effectively the same. The next part of the problem, I want this to be the final stage of this problem, and then we can break for lunch, and we'll try and work on an infill drilling one single-phase liquid this afternoon. I don't think we'll have time to go through all of it, where we go from the 40 to the 20 to the 10s, because it's just going to take a lot of time. But we'll try and go through the 40s to the 10, or 40 to the 20, and I'll make copies of all. I cleaned up my hand calculations while I was in Trondheim, and I got nice methodical. Even I could follow it now. It took me a long time to get my notes straightened out, because I did the work about 3 months ago, and I couldn't remember what I was doing, and I organized it, I think, a little better, and I found a couple errors in the calculations too. But how you're going to calculate cross flow, okay? You make a production forecast like you did before, but let's everybody do it. And what you're going to do is the QI is equal to your QI layer 1, your plus QI layer 2, and you stick it in that format so that you remember it. In G in the denominator is G1 plus G2. Not the initial again. Let's stay consistent. We're still looking at flowing pressure of 100 pounds. So this is the flow rate against 100 pounds, and the gas at a 100-pound flowing pressure. Because it's a single-layered system now, the B value is going to be 0.4. Now, cross flow will behave identically equivalent to or the sum of the two layers' properties. Okay, sum of the KHs or the sum of the. It's normally presented in literature. You just you sum the KHs and divide by total of KH at the total H, and that'll give you the average K. Well, that isn't any different. Just adding the two deliverabilities together. One advantage here, though, is if you had a problem where you was treating one layer with a 0 skin and the other layer with a minus skin, it's exactly rigorous. Just add the two Q's together, because you can get caught in a real bind trying to say, well, the KHs is this. Now, what's my equivalent skin? Don't worry about it. This solves it immediately by just adding the two deliverabilities together. And if you had different slopes, you just plot the back pressure curves, stabilized back pressure curves, if they got different slopes. At a common delta P squared, you add the Q from each one, add them together, you plot it, and you're going to get a slope in between, and you're going to get a composite back pressure curve. That's what you'd use for the commingle. Very simple. Again, if you didn't look at it this way and you tried to use an average K, you're going to be totally confused about what's the equivalent skin of this system. You do it this way, you have a way of going backwards in order to exactly calculate if you want to. Otherwise, you'd be bogged down in you're trying to derive a new analytic expression. And just add the two G's together. Go ahead and make the forecast. And I'll put them down. Year one, the cross flow, with the rate. 8,051. Okay. Okay.
5,736.
Yeah, well, just give me consecutive digits.
4255. 3259. 2561.
Wait. The 2561? Let's see, that's year 5. Okay.
Year 10, 995. Year 15. Year 15,
Okay.
502. Year 20, 294. Year 25, 189. 189.
All right.
Year 30, 130.
Okay.
Year 35, 94.
Okay.
Year 40, 70.
Okay.
45, 54.
All right.
And 50, 4, 3.
Okay. Everybody has a chance to kind of check their numbers, and that's the difference. And that's the difference between your cross flow and no cross flow. And you can see this is the cross flow case. That assumption in the early times is drastically going to affect your economics, isn't it? If you develop a reservoir and it is no cross flow, you can drop off the end of the table. What are you going to say? What's going on? Well, we got less in place than what we thought. Or all kinds of explanations, see. Which gets back to the point, again, I think a base case has got to include no cross flow for what you're doing. The results may be frightening, but I'd rather know at the beginning. Management may not want to look at it, but as an engineer, it's your responsibility that you have to give them what you. It's better than taking these numbers or these numbers here and doing a risk analysis. Okay, it sounds like you have really improved things, or you're applying the most advanced technology. Your skirts are clean now because you did risk analysis, and all I'm saying is this is the risk. That you have no cross flow as opposed to cross flow. That's the risk. And again, you might find out that the properties could be such that it don't make any difference. That the ratio isn't 10 or 20 like this, it's only 2. And then it'll behave like a single layer system. If you run it cross flow or no cross flow, you get about the same answer. Why don't you go ahead now and go through the exercise of using the Kuhn time equation, calculate the Kuhn at the end of 5 years, and then what the P over Z would be for 5 years, unless you've already done it. If you've already done it. Okay? All right. Cross flow case, the cumulative production after the end of 5 years is over 10 billion. And for the no cross flow case, let me add them up here. In no cross flow, The cumulative production is going to be 6,246,000,000. And the P over Z $295, the PSIA, and there 2. There's going to be 1,059. Yeah, this is the one that you'd see at the end of 5 years if there was no cross flow and you shut the well in, as compared to the. This is what you'd see in terms of pressure. And of course, you'd have produced a lot more gas. 10 billion versus about 6 billion at the end of 5 years. And so you see there is a big difference in the results that you get, whether you assume crossflow or no crossflow. Everything's identical. All the other data is identical. The well deliverabilities, the Ks, the Hs, the gas in place, everything's identical for the two problems.